Welcome to the course on FPGA based signal processing systems. The lecture 18 is based on the blocking and non-blocking assignments. So in continuing with the sequential circuits, it will be very useful to learn this difference between this blocking and non-blocking statements. So let's see that examples of the blocking and non-blocking statements here. So first example I took is to swapping content of a register. Okay, so a 16-bit this module contains the register which is having the 16-bit code. So the first 8 bits and the next 8 bits need to be swapped. The first 8 bits should be moved to the next 8 bits, and then next 8 bits should move to the first 8 bits. So here we had taken the module and the module name. So we have just simulated that in the to show the output in the simulator. So the module name here we didn't take any input in this case, just it is the stored value is getting swapped here. So the reg declaration of the code is the code is a register which is having the 16 bits here, and the clock. So we have initial begin. The code is initially to 0 and then clock is 0 to initialize this the code and clock. Later this is always at the passage of the clock, as we do in the test bench, because this code needs a clock, some hash 100 and clock, not clock. Let's see this the main code of this. Always at the passage of the clock begin, swap it, that 8 and 15, that 8 to 15 here, code of 8 to 15 to be transferred to the code at the place of 0 to 7. So considering this this first one here, you have 0 to 7 and 8 to 15. This is a 16-bit reg the code which we have mentioned in the Verilog code module. So assuming that this content has AB and this content has CD. Okay, so now we are trying to swap it. The code, whatever is the content available over here is equal, that is assigned to 0 to 7 here. The first code says this. You notice that the blocking assignment is used here, and then the next statement says that transfer this over here. Okay, so 0 to 7 equal, that is assigned to 8 to 15. So end, will it happen, that swap can happen in this case or not? Okay, so let's see this the stimulus, or the what is the content needs to be stored for the register. The content as hash 100 code is 16-bit ABCD. Okay, so we have given this as ABCD and a 16-bit. So display this with the monitor time and code. So will this swap, this end module, the swapping will happen or not? So look at this in the blocking assignment. So 1588 is that containing AB. Okay, the content, that is 4-bit A and 4-bit B here, if you represent in binary, that's 8-bit. And then that AB is transferred to CD. Okay, yes, it is the code what is there in the when it advice at the passage of the clock. This code whatever is having the content AB is transferred to 0 to 7. Yes, it is transferring to 0 to 7. Then it is an immediate assignment. The blocking assignment evaluates it and assigns it to the 0 to 7. And next, because it's within the always block, so the execution will be sequential. So the next one, the 0 to 7 whatever is available, because it is updated now, code 0 to 7 which is AB now, and that is copied to 15 to 8. So that means AB will be again copied to AB, but the two of them are not getting interchanged or swapped here. So because of the blocking assignment. So let's say it will swap. No, it will not swap here, because A and B, AB will be copied in both the parts of the register. So let's look at the output here. So it's given initially, that is, this is the clock, and the code output, it is 0. Initially we assign it 0 till 100 nanoseconds, and the clock is generated for 100 nanoseconds and for on period, and 100, this is, so you have the 200 nanoseconds clock. In that, let's see the content which is not getting swapped. So AB and AB will be repeatedly in the content, so this is not getting swapped. So the same thing would also be observed in the output code which is printed in the log file. So now the other choice, the same block, let's try this also, the clock code, and initialize this code, and then always that this is same as the first part which we had done. And now we try to make this sentences, the statements, in different order. First we did 15 content to 0 to 7, and then 0 to 7 to 18. Shall we interchange that? I mean, shall we make this code order change? So, okay, so this statement 0 to 7 code, now this is the code. Let's see whether it gets swapped. The 0 to 7, so we have the CD, the content we have given it in the, like in the previous case, which is copied over. So 0 to 7 is copied to 15 to 8 in the, because it's a blocking assignment again. This is evaluated and assigned immediately, 8 to 15. After that, the second statement gets executed. So 15 to 8, in this the content is now copied to 0 to 7. That means now it is CD, and again this is getting copied to CD. So again the case of blocking, the input is this. If you monitor whether it will have the swap, so it won't be swapping C and D. Okay, so this is ABCD is not a swap, so it is copying both. The CD is copied in to a 16-bit register, both 0 to 7 as well as 8 to 15. So let's see the same thing in the output, that is CD is, this is code is 0 initially. When the clock edge occurs, this is just copied over here, so that is maintained, that CD. Every passage of the clock, same thing is happening, so CD is maintained over the clock change. So the same thing can be observed here as well. So you can see the CD and CD, so that is over everywhere in the, at 100 whatever is there, it gets maintained. So there is no change in the change with respect to the clock. So this is due to the blocking assignment. So blocking assignment evaluates at right hand side and immediately updates the left hand side, so it's immediate assignment. So now how do we solve this swapping problem here? The code remains here same as the first part of this, that is 16-bit register and the clock, because we are using them in the inside the always block, so we need to declare them here also. Always at the rate clock equal to clock naught. Now we just simply change this always at the passage of the clock, begin the main code with 0 to 7 less than or equal to code at the left hand side 15 8, and the right hand side we can just notice with the previous code, it is just 0, the non-blocking assignment is used. So here end, initial, begin, so give them this ABCD and plot them, also the T code and time with respect to the time. So end module, whether the swap can happen or not. Yes, here what is happening, so the 0 to 7, the content here is CD. Yes, the CD is evaluated, it's not assigned immediately to 8 to 15. So 8 to 15 has still after evaluation, it has this AB content. Okay, so, and then comes the second code, and at the same simulation time, the 8 to 15 has AB. Okay, so this is also evaluated, these two CD and AB are evaluated. The assignment takes at the same time, that is at the end of the simulation time, that T equal to 0. So the here, because there is no delay involved in it, so here we have, unless until we specify here this is 100, the input is given at hash 100. Okay, so at the end of the simulation time, current simulation time, that both the values are getting, so 0 to 7 we have CD which is going to 15 to 8, and the A baby is going to 0 to 7. So there is a swap. Yes, it is happening here, the swap due to the non-blocking assignment. So it is not an immediate assignment, this is the late assignment, the perfect example for the non-blocking statement which helps in the swapping. So if we change the order, if we change the order of this, making this statement first and then second this statement, the same thing can happen. So here anyway, the output we can see at every clock edge for the first code, it is changing, that is CD AB, AB CD, and then you can see CD AB, every clock edge the output gets changed over here. So every clock edge, whatever was there, that was ABCD first, and then this is changed now to CDAB, ABCD, and then CDAB, and this gets changed. So we can observe the same thing over console also. This is the 4 bits which is getting, this is AB, and then this is CD over here. So CD AB, and then next it is changing ABCD, and so on. So there is a swap occurs with every clock edge because of this non-blocking assignment. The order change of the code in the non-blocking assignment itself, yes, it would the initialized the first part of the code, I kept it the same thing that it is to for completeness. Always hash 100 clock is equal to tilde clock. In that case, yes, we have the first, you can see the order change in the code. So 15.8 has AB, which is moving to 0 to 7, and CD is moved to 0 to 7 is moved to F8. So the order doesn't matter here. This is first evaluated and it is not assigned. It is evaluated again. It's not assigned. So after this evaluation, this 0 to 7 gets also the whatever in the right hand side, and 8 to 15 also gets the right hand side content output here. So here tested with this code, same input ABCD. So the in module is yes, the swap can occur at this point. So these output you can see, this is CDAB, ABCD, yeah, this is happening at every clock edge, that is passage of the clock. Here mentioned is the passage of the clock. So the same thing, that 100, 300, 500, 700 and 900 nanoseconds. So this is CD, C and D, and this is A and B, that is 100. After that it gets changed A, B, and then C and D. So the change can be observed, the swapping occurs in this case. So this is the difference between the blocking and non-blocking assignment. So the right hand side is evaluated, it is assigned immediately in the blocking assignment. So considering this for loop for the and other loops we have used, example how to create the clock and how to use it for designing this counter. So using that counter for designing the counter, how to use this for loop, and how to use the repeat loop, also the forever loop, and so on. So these loops can be use it to design a counter. So yes, this is a 7-bit counter. Here it counts up to 0 to 127. So the code we have discussed in the previous lecture, that is just giving you the simulated output here. How module, this module count display, that is for count is declared as integer, and initial begin for loop. Let's look at the for loop. The count is 0 initialized and is the first expression, and the what is the condition, less than or equal less than 128, count equal to count plus 1, and then display the count. So here is the integer, the count, which is of 32-bit. Okay, so it keeps incrementing till 127. So the count becomes 127. So that we just have, so the 7-bit counter have this 0 to 127 outputs here. Okay. So let's see the output of the Vivado that is simulated log file. So count 0 and count 1, 2, 3, 4, and it gets counting up to this here 40, and then it goes up to 60. See here the outputs printed over here instead of a waveform. I just had this getting printed up. It goes up to 127. So the count value is going up to 0 to 127. So the delay is, there is no delay in the increment. So that's very small time it takes to count equal to count plus 1. So it is in a picoseconds resolution. You could see them here, the printed 10 to 127. So this is using the for loop. This counter can be a simple one statement with the for loop can do the increment can be simply used as count equal to count 1, count plus 1. So the counter can be designed with this count is an integer here, and the condition can be specified in the for loop. Similarly, we can also use this while loop. The module count while integer count and initial begin here count is 0 initially, and while repeat this operation till this count is less than 128. So this is the logic condition. If you remember, that count is 128. So the begin display count equal to count plus 1. So we keep incrementing this counter, and this begin ends over here. The one which is before is ending over here. So this is using the while loop. If less than 128, yes, the display, you could see the same thing here, 0 to 20, and then 40, it keeps incrementing, and then 80, 128, so 0 to 127 it counts. And then if you continue that, I mean, you want a counter which needs to be incrementing like this from 0 to 127, and then reset it. You can reset even with after 127 and continue it, and this signal will be useful in many of the applications, like generating sine and cosine signals inside the FPGAs. So that will be useful in the this counter would be useful to generate a phase of the cos signal or sine signal. And similarly, the case repeat loop, with the repeat loop module count rate integer count equal to 0, initialize it and repeat this for 128 times. Okay, so begin display that count and count equal to count plus 1. So it displays it one time, 2 and 3 and 4 and so on, and it displays up to 127. So, okay, so but it increments that state unto 128. So can we see the output of this one really the same as the previous examples? So we have seen the for loop, while loop, as well as the repeat loop to design the counter. It can be used for the counter designs. Also the forever loop, I have used this forever loop for a 7-bit counter, which is 0. You can see the initial begin, which has count 0, that is as usual in the count needs to be declared as 0. Then the forever loop, in which we have what should be done, count it needs to be incremented continuously till what condition that we have this is the display over here, this count equal to count plus 1, how long we need to do it. So when you use the forever loop, that should be a condition, either you stop this counter operation or put a condition here, if count is equal to this 127, then $finish. Okay, so this is the $finish needs to be this in the forever loop. We need to include the to stop it at 127. So it will count from 0 to 127. If you have not used it for the repetition of the as I given in the previous example, you can use this for till reset and then repeat also can be done, that design will look into it. So for counting it 0 to 127 and then again reset it and then start from 0 to 127 and reset, and this could be done with slight modification in the code. Like this is for one cycle of the count, that is equal to 0 to 127. So in all this example we have taken the condition for the stop at 127 and start from, that is 0 here. So the output it's similar in line with the same with the previous cases, but because we have used the dollar finish, it is also a dollar finish is used after the 127. So this is the output printed in the log file. So with this the different loops can be used for this counter, okay, counter design. And there will be anyway synchronous digital synchronous sequential circuits. We will be designing the counters, how we can design as a counter, how can we see that counters as a state machine, and all those things will be dealing in the coming lectures. So now coming to the sequential blocks, again this in the sequential circuits. So a few examples related to the simulator and the time instance in the simulator, and how the statements, if you use the time delay, how it is getting executed. If you don't introduce the time delay, how this blocking and non-blocking assignments. Again, a few more examples would help to understand this with the timing control. Okay. So the sequential block without any delay, I mean we have not included any delay in this example. So module which is called the module name as sequential block and doesn't have any input, it is just assigned and check the simulator value. So here it is having xy and zw. Okay, so z and w are 2 bits and x and y are the single bit. So now the initial begin, what we had just this displaying this x, y, z, w. Okay, so what this within the initial block we are doing. So we have x, y. So we first have the code here, which is x is 0. Okay, so within the initial block begin and displayed that whatever with respect to that, and it is a blocking assignment. Again, x equal to 1 bit 0 and y equal to 1 bit 1. Okay, z is equal to concatenation of x comma y, okay, and w is y comma x. Okay, so this should have this 0 1 and this is 1 0. Okay, so here which one will be executed and what is the order in which the execution will be. So here this begin ends over here. Okay, within the initial block again it is sequential. Okay, so let's see the output of this. Here waveform is giving at 0 time instant. So there is no this x is assigned 0, this here you can see that, and y is given 1. Okay, 0 and 1, and the value z is given x concatenation y. Okay, so x is 0 and y is 1, so it is concatenating x y and giving that at the same instant it is 0 1. Okay, and the next one w, it is given yx, if you recall. So it's 1 0, you can see over here 1 0. This is again the concatenation. So it is also happening at the same time. So it is evaluated, x is assigned and y is assigned at the simulation time, at the current simulation time, and this is evaluated and assigned. You can see the one, and also this within no time here it is 0, it is 1 0, it is changed to 1 0, this y and z here. So it's a blocking assignment and sequentially happening, there is no timing control in this case. So if you look at the even in the picosecond variation of this, it happens at the 0 time. So with the delay, if we introduce a delay, what happens in this example, that the same example module will have this range x, y and 1 0 z w, the same variables, initial begin. Let's slightly change the code of this here. X is 1 bit 0 and y equal to 1 bit 1, and putting this hash 5 here. Okay, and this is with blocking assignments only, and hash 10 z equal to x comma y. Okay, so then 20 y w equal to y and x. So what is happening here? Then if we give this timing control, so this is just pushing this evaluation itself. If you allow the timing control at this point, that is hash 5, evaluation itself getting late. Okay, so that means if at time 0 there is no 0, x is getting 0, that is completed at this simulation time t equal to 0. When you put hash 5, that 1 will be evaluated and assigned after hash 5, that is at time unit 5, and after 5 this is next will be hash and this is 15 plus 10. Okay, so at 15 time units, x and y are concatenated and assigned to z. So the evaluation and assignment getting delayed. This is detailed evaluation. And hash 5, 10, and then it is 15. Okay, 15 here, and then 20. So this is 5 and 10, 15. So at 15 it gets assigned. After 15, 20 time units. So that 35. This is w. It's getting y and x concatenated. So it's a sequential, and the time delays are getting added for delay evaluation and assignment. So let's see the output here. So the x is getting 0 initially, there is no timing control, and y is getting at 5 nanoseconds, and is it the concatenation one after that 10 nanoseconds added. So at 15 this becomes 0 1, and z is getting the one at 35, another 20 time units from here. So it's going to 1 0. So we can see that in the previous case it is happening at a 0th instant. Okay, so now with that, with help of this timing control, that delayed evaluation with blocking assignment, you can just delay this assignments. So evaluation and assignment as well. So here that is a blocking assignment can be seen at 5 and then 15, and then here at plus 20, so 35 the change. So the log file shows that at 0 there is no, I mean it doesn't get any output, that is unknown. At 5 also, at 5 you can see it is y is only getting the 5 nanoseconds, and z and w are not stable, x is still have this, y doesn't have this values. So after that 15, yes, this still that w didn't get anything here. So at 35, because that is not even evaluated, it is delayed. So here is 0 1, and that 0 1 is maintained after that, and then w has 1 0. Okay, this is with the timing control, the blocking assignments. So if you have the multiple initial statements, so in the test bench also we use this, which one will be taken first, right? That initial, if these initial statements are concurrent, yes, but how these statements are getting executed. Okay, so the multiple initial statements take the model stimulus. There are variables used here, x, y, a, b, m, and initial first m is made 0, and then initial begin, there is another initial hash 5 a equal to 1 bit 1, there is 25 at 25 hash 25 b is made 0, and this is n. So there are two initials. Apart from that, in this code we can have there is another full code. Let me give you the full code. The third initial block, which has begin at hash 10x, it is 1 bit 0, and then hash 25 it is having 1 bit 1. So this is end and display here. This is hash 50. After that it is going to be the dollar finish. So now we have this two initial in the previous slide, and another 1 2 3 again 5 initial blocks here. So how this statement, when we have this timing controls getting initiated, those are concurrent. Okay, so at time t equal to 0, it checks that here we have this in the first initial block. Yes, there is a time t equal to 0, m is to be assigned 1 bit 0. Okay, is that next? If you see the second Next one, which is if we come to the coming to this previous case, next 5 at A is supposed to be assigned 1. Okay, so that 0, after that this is the 5. Will it execute the next one hash 25, or because this initial blocks are concurrent, it is looking for the next initial condition here. So in this case we have hash 10 before that. This is 10. So at 5, from the previous initial block A is 1 bit assigned, and then at 10 this x equal to 1 bit 0 is getting executed. So after 10, let us see, will this 25 be executed? No, and because it is here, we have, this is again the block which has 25. Okay, so the hash 25, this 5 is taken, and the hash 10 from the next initial block is getting executed, and then after this, if you see, next immediate assignment evaluation comes at the hash 25. So first 5, then go to the next initial block, execute that, that is at the 10, from 0 to that 10. After that, here you have this, after 5 you have this 25. Okay, so here, so this is 5 plus 25 at 30, this B is getting to be 0. Okay, so after this, then comes the block here, that is hash 25. It is from, no, after 10, it is waiting for the next time. So what we get is after 30, this is 35, this is from the initial one. So this 25 plus this is from here. Okay, so this, and this one from the previous initial condition. So this y equal to 1 is getting evaluated and assigned. So this display hash 50, yes, it is dollar finish. After that, that is from 0th time, this is going to refer this hash 50. So it is this 0 time, and then it looks for the where this next 5, and with 0, then next 10 comes into picture, and then goes back to the next initial condition, it executes the second statement, and then next 25, it is here 35, y equal to 1 bit 1, after that 0 at 50 get the dollar finish. So this is the way this even though you have the multiple initial statements, it looks for the simulator time which is referred, and then it keeps switching between this initial blocks for execution, depends on the time which is specified. If there is no there is no time specified, the initial blocks that are executed sequentially, and then and every initial block is concurrent. So the output which can be observed here, that is at 10 it is 0, and this is at 35, you can see this is becoming 1, and AB, this is at A 5. Okay, here the first one, and then you can see the 30 and 35 other blocks also. Okay, M is already getting 0 at the initial value, no timing info, no timing is specified for this. So that, so 5, and then goes to 10, and then comes back to this here 30, and then 35. So this is an order which those statements are even spread over the initial blocks, in different initial blocks. So this is how this the statement execution takes place. So I have given this already. So with with this one, so we have seen the blocking and non-blocking assignments in this how the swapping example, the immediate assignment and late assignment. If we introduce this blocking in this the previous example, if we have the blocking assignment and timing control, how this simulator moves and to keep tracks of the time, the statement for the statements to be executed. Also, we have seen different loops can be used for this counter design as well. So we have shown that with one cycle, the counter can be for one cycle counting, how this loops can be used, and this can be repeated also with the reset statement. One more reset statement can have this counter repeatedly expanding to the different number of cycles as well. Thank you.